We have so far covered ring theory in this course, and now in the remaining part of the course I will study fields. So we already know what fields are. So let me remind you what fields are. Fields are special kinds of ring, right? So F is a field if it is a ring in which or such that F minus 0 0 is the additive identity element as always. F minus 0 is a group under multiplication. So in the remaining course we are going to study rings which have this property. So though these are just special cases of rings, their study has a very different flavor from the study of rings, as we will learn in these remaining videos of the course. So let me first give you a collection of examples that we will be dealing with often before we continue and study more properties of fields. So first part of this video I am going to study examples. The examples that we are already familiar with are Q, R, C. We are also familiar with Z mod PZ, where P is a prime number. Right, in the beginning of the course, when I defined quotient rings and we discussed Z mod NZ, we proved that Z mod NZ is a field if and only if n is a prime number. So in the rest of the course we are going to use P to denote prime number. In this field we denote usually by FP, F written with this special symbol. FP is Z mod PZ. So this is different from the remaining examples that I wrote here in the sense that this is a finite field. This is a finite field, right? Finite here simply refers to the fact that there are only finitely many elements. So that's all. So there are only finitely many elements in FP. We call it a finite field because of that. Q, R and C, the field of rational numbers, the field of real numbers, the field of complex numbers are not finite fields because certainly they have infinitely many elements. So there are two classes of examples here I am discussing, right? So Q, R, C are subfields of C. So unlike in the case of rings where we have subrings but they did not feature prominently in our study of rings, there we looked at ideals, homomorphisms of rings, quotient rings. These were the important operations and objects in the study of rings. Whereas in the study of fields, we are often going to study subfield of a field. So rather we are going to study pairs of fields where one contains the other. So let me quickly tell you what a subfield is. This is something that you can guess. Just like a subring of a ring, we say that a subring of a ring is a subset which is under addition, it's an abelian subgroup, and it is closed under multiplication, right? So it's basically the sub object in the category of rings. Here subfield is exactly the same. So let define subfields more generally. Let K be a field. The typical letters that I will use to denote fields are going to be K, capital F, capital L and so on. So this is the definition. Let K be a field, a subfield. So maybe I should write this separately. This is a very important definition for us. So definition, let K be a field, a subfield F of K is a subset of such that which is a, so let me write satisfying the obvious properties, right? 1, F is a subgroup of the additive group right. So F is a field, in particular it's a ring, so it has two operations, we call them plus and times. So it is a subgroup of the additive group K plus, I should write. So if you forget the multiplication on K and only consider the addition, it's an abelian group, F must be a subgroup of it. F minus 0, so because F is a subgroup of the additive group, F contains 0, and if you remove it, it must be a subgroup of the multiplicative group K minus 0 cross. Okay, so simple. So it is a subgroup in both senses. It is an additive subgroup as it is, and after removing 0, it is a multiplicative subgroup. Okay, so now let me make some convention here. So convention is, or rather we will always assume, see, remember a field is a ring, and in this course our rings are commutative with 1. So rings contain 1 and the multiplication there is always commutative. So these assumptions carry over to fields because our fields are also special classes of rings. Now in a ring it is conceivable that 0, which is the additive identity, is equal to 1, which is the multiplicative identity. So in other words, you can have 0 equal to 1, in which case this ring is the 0 ring. We will not consider that as a field. So in a field F, we have 0 is not equal to 1. So the additive identity is not same as the multiplicative identity. So our fields always contain at least 2 elements, right? So this is an important statement. You cannot have a field with only one element, because in that field 0 must be equal to 1, which we are eliminating. The point is, when you remove 0, this follows the, actually I should say we will always assume this, in fact we will have this, because it's a ring such that F minus 0 is a group under multiplication. A group is supposed to be non-empty, so if you remove 0, if it has to be a group, it has to be non-empty, so it must have identity. So in fact, it's not just that, we have the following. So I will write like, we have the following, right? So that's not an assumption, it is a consequence of our definition. Okay, so now the most important terminology that we will use in the rest of the course when we study fields is, if F is a subfield of K, we say that K is a field extension of F, and we write this as Kf is a field extension. So various notations we will follow. Field extension, we write K over F. Do not confuse this with the construction of a quotient ring. This is not that, so it's somewhat confusing. So, and I will generally try to avoid this notation, but you might see this sometimes. K over F, when we are talking about fields, is just a notation. It is just a short for K is a field extension of F. We will of course write F, K contains F, or F is contained in K, is a field extension. So these are various notations that I will use. So this is one, and another more pictorial description is this: K, and we put a vertical bar, and we'll put F is a field extension. Okay, so as I said, the study of fields has a very different flavor to the study of rings, where when we studied rings, we looked at ideals in a ring, we looked at quotient rings. When we quotient an ideal, we looked at morphisms, homomorphisms of rings, and various other issues, other constructions and objects. And subrings were not that important, right? If you go back and see the ring theory part of the course, we really didn't talk much about subrings, though we learned what a subring is and we saw examples. It was not a prominent aspect of ring theory, whereas the entire field theory that we are going to study is really a study of field extensions. So these are the important objects for us. Field extensions are the objects that we study. So what I am trying to say is that we studied a ring on its own in some sense, whereas we do not study a field on its own, but we study its subfields, or how a field sits inside another field, and so on. So our objects are not just fields but field extensions. So that means these are pairs of fields. F is a subfield of K, and we will say that as K is a extension field of F. Okay. So now what I said earlier was that Q, R and C are subfields of C. Of course they are. So examples of field extensions: so of course we have C over R, R over C, we have R over Q, we have C over Q, and we have not yet learned of any field extension of Z mod PZ, right? So there are field extensions of Z mod PZ, and that's going to be discussed when we study finite fields explicitly. We are going to study finite fields in a few videos. So there we will study field extensions of Z mod PZ, but for now let's look at some other cases. So for example, you can have Q, so I can introduce one obvious extension field of Z mod PZ in the following way. So let K be a field consider the polynomial ring Kx. The quotient field, or the field of fractions in the language I used in the earlier part of the course, the field of fractions of Kx is denoted by K round bracket x. Okay, so K square bracket x is the polynomial ring, K round bracket x is its quotient field. So this is called a function field. So then of course this is a field extension, right? So this applies for any field K. So in particular we can consider Z mod PZ and include it in Z mod PZ bracket x. What is the typical element in K round bracket x? It will be of the form f by g, where f and g are polynomials in K square bracket x. So this is always a field extension, though if you start with Z mod PZ and you construct this new field, it's no longer going to be finite field. It will have infinitely many elements, because remember, polynomial ring is already infinite ring. So when you take the field of fractions, it's going to also be infinite. So we will study later field extensions of Z mod PZ, which are also finite fields. But this is an extension that we can construct for every field. And this we are not going to study that much. These are examples of what are called function fields. The terminology comes from algebraic geometry and analysis, where these elements of this can be thought of as functions, because a polynomial is a function A ratio of two polynomials also is a function, but that's not going to be studied by us in detail. So now another construction I want to give is, so let us now start with an arbitrary field extension. Let K be a field extension of a field F. As I said, my main object of study in this course, in the field theory part, is field extension. So K is an arbitrary field extension of another field F. Typically I use F for the smaller field, K for the bigger field. Now let us pick an element of K. Let's call alpha. Let alpha be an element of K. So we are going to, so we have K and F here. We are going to construct or consider a new field which sits between F and K, and we are going to call this F alpha. And what is this? So the picture will be K, F alpha, F. So this is what we call an intermediate field. So in particular, when I write this, what I mean is F is a subfield of F alpha and F alpha is a subfield of K. So this data is represented like this. And what is F alpha? F alpha is simply the smallest subfield of K containing F and alpha. Right, so this is a field that is supposed to contain F and also alpha, and we look at the smallest such field. In fact, it is equal to the intersection of all fields that contain all subfields of K. I should say, I should remain within K here. I'm only doing this between K and F. So intersection of all subfields of K which contain F and alpha. One can check that that intersection is actually a field, because if two elements are in that intersection, those two elements are in every field. That means the sum and the product is in every field, the inverses are in every field. So they will be in the intersection. Yet another description of F alpha, elements of F alpha can be described as so as follows. Let me write like that and I will describe it now. So let us construct such a field. What are we supposed to make sure? We are supposed to make sure that capital F is contained in this and alpha is contained in this. So if alpha is in F alpha and F is in F alpha, that means all expressions of the form an alpha n, an minus 1 alpha n minus 1, a1 alpha plus a0 are in F alpha with whenever ai or all of these coefficients an, a1, a0 or an f. This is clear, right? Because if alpha is there, F alpha is a field. So this alpha power n is there, alpha power n minus 1 is there, alpha is there, and f is inside it. So an minus 1, a1, a0 are all there. So all linear combinations are like this are going to be there. This will happen as soon as this is a ring. I am not looking at the smallest ring containing f and alpha. So I also must have ratios of this. So these are polynomials. If you recall polynomials that we studied in ring theory, these are polynomials in alpha with coefficients in f, right? Exactly, that's what this is. These are polynomials in the element alpha with coefficients in f. But this is only one consequence of f alpha being a field. F alpha also contains all ratios of polynomials of the above form. Why is that? Remember, now we are in the realm of fields. It's any element that's non-zero is going to contain its inverse also. So f alpha is a field. As soon as you have such a polynomial which is non-zero, 1 over that, which is the multiplicative inverse, is there. That means we have to take all ratios of polynomials. Of course, denominator has to be non-zero. That goes without saying, right? We take ratios of f by g, small f by small g. So f alpha by g alpha. So let's call this f alpha, small f alpha. That means you are thinking of a polynomial in a variable capital X, an xn, an minus 1, xn minus 1 and so on. Then you are plugging in alpha for x. Similarly, you take g alpha whenever g alpha is non-zero. So that's what we are saying, is that f alpha contains this set f alpha, g alpha, where fx, gx are polynomials in one variable over the field f, and g alpha is non-zero. This is forced for us because f alpha is supposed to contain capital F and alpha, and it is supposed to be a field. So it must contain all such ratios. Now the point is, as an exercise, the set above is actually a field. So you take such ratios f alpha by g alpha, where f and g are polynomials in one variable over capital F, and of course g alpha is non-zero, then it is in fact a field, because 0 is there. You can take the 0 polynomial for f and constant polynomial for 1 for g, then you get 0. You can take f and g to be both 1, you get 1. If you take two such things, you add them, it's another polynomial ratio of another set of polynomials. Multiply them, that's also a rational polynomial. So it's very easy to check that it is in fact a field. Hence, f alpha is equal to this, right? It is supposed to be the smallest field that contains both f and alpha, and we have described now the concrete description of elements of capital F alpha. So this is a very important construction for us. Every time you have a field extension and an element in the bigger field, we have an intermediate field containing both f and alpha, and in general it is smaller than k. Of course, in some examples it would be equal to k or equal to f even. So what are the examples of this? So for example, if you take C over R and you take I here, the imaginary square root of minus 1. What is R bracket I? This in fact I claim is C, and I will leave that as an exercise for you, because what is R bracket I? In the description that we gave, it is going to contain Fi by Gi, but every complex number is of the form a plus ib, where a and b are real numbers, right? So C is already a plus ib, this we know, where a, b are in R, but Ri will certainly contain them, because Ri is you take all polynomials with rational coefficients. In particular, you can take the polynomial a plus xb, right? So this is in Rx, because a, b are in R. If you take this to be fx, what is fi? This is a plus ib. So just taking the polynomials, we do not even need to take ratios. This will be in Ri, right? So for all ab in R. So a plus ib is already in Ri, but a plus ib is equal to C. So Ri is equal to C. On the other hand, what is R bracket square root 2. R bracket square root 2 I claim is R, and this is an exercise for you. R bracket square root is R because what is this? These are ratios of polynomials by the description I gave there. These are ratios of polynomials in one variable such that g root 2 is non-zero, right? But remember, if f is a real polynomial and you plug in root 2, you get nothing more than, you get actually real numbers only. So this set is in R, but R obviously is contained in R root 2 by definition. So R is contained in R root 2, R root 2 is contained in R, so this is the equality. So I more or less finished, completely solved these exercises, but these are simple examples, and in fact we will see later that if K is an intermediate field of the extension C containing R, then we must have that K is either C or K is R. So what I am saying is that if you have a field extension, if you have the field extension C over R and K is in between, either these are equal or these are equal. Okay, so there is no field that is properly between C and R. So some more examples let me do. So second example, so you take R and Q. You take R and Q. Now you can take root 2 here, which is not here, and you can consider Q root 2. That's K. So Q root 2 will be an intermediate field, and what we can do is we can describe the elements of Q root 2 as we have done before, but we will have a more convenient description, more simple description later. But this is actually not equal to R. That's all I will say for now, and K is certainly not equal to Q. So this is a proper intermediate field, and both of these statements are clear because root 2 is contained in K, right? Root 2 is contained in K by definition, but root 2 is not in Q. So Q is strictly bigger than Q. K is strictly bigger than Q, I should say. Similarly, R contains many real numbers which are not going to be expressed in terms of Q root 2, because Q root 2 is only things like this, f root 2 by g root 2, where f and g are real rational polynomials. For example, one can check quickly that root 3 is not in K, and similarly, so this implies this, because root 3 is not in K but it's in R. Okay, so these are important subfields of C. So the two classes of fields that we are going to study in detail in this field theory course is subfields of C. They are called number fields. So these are called these are subfields of C. They are number fields because complex numbers. So number refers to complex numbers. These are fields containing numbers, complex numbers, and we are going to study finite fields. So the two important classes of the fields that we are going to study are number fields and finite fields. Initially we will do some general study of properties of fields, then we will look more closely at number fields and finite fields. There are lots of other kinds of fields, but we will refer to them sometimes in examples, but our primary focus is going to be on number fields and finite fields. Okay, so let me now introduce a very important notion and then stop the video, and we will continue with that notion next time. So this is an important definition for us. So let K over F be a field extension. So this is the shortest way of writing, and I want you to get used to this. Again, let me remind you that we are not talking about quotients at all. This is not the ring quotients of rings that we've learned earlier. This is just another short way of saying that F and K are fields and F is a subfield of K. So let K over F be a field extension, and let us choose an element alpha in K. We say that alpha is algebraic over F. We say that alpha is algebraic over F if there exists a polynomial in one variable over capital F So remember, capital Fx, capital F square bracket x is a notation that we have been using in this course. It stands for the polynomial ring in one variable x over capital F. So there exists a polynomial small fx in capital Fx such that f alpha is 0. Okay. So algebraic if alpha is a root of a polynomial, that is alpha is algebraic over f if alpha is a root of a polynomial over f. That's a convenient way of remembering this. And I want to stress again, which I will do again and again, that over capital F is an extremely important part of the terminology. Alpha is algebraic over capital F, because the same element may be algebraic over some field and it may not be algebraic over another field. Okay. So, and continuing the definition, we say that alpha is transcendental over again F. Over is again, over F is an important part of the transcendental over capital F if it is not algebraic, that's all. So if there is no polynomial over capital F that alpha satisfies, or in other words there is no polynomial over capital F for which alpha is a root, we say alpha is transcendental over it. Okay. So now let me give a quick set of examples, then we will stop. So let's take the extension R over Q. For this example, we say first that root 2, we see that root 2 is algebraic over Q. Why is this? Because root 2 is a root of x squared minus 2, which is in Qx. Okay, so root 2 is a root of the polynomial x squared minus 2. Similarly, root 5, fifth root of 2 is algebraic over F, algebraic over Q. That is because we can consider the polynomial x power 5 minus 2. Right? Similarly, we can consider I. So I of course is not in R. So if you consider the polynomial, the field extension Q, C over Q, I in C is algebraic over Q. Remember, all this study needs to fix a field extension a priori. You fix a field extension, you consider an element in the bigger field, and you look at polynomials over the lower field and look at any polynomial which may have the element as a root. Here it's of course algebraic because it's the root of this polynomial. Going back to R over Q, you all know the elements pi and e that are defined using some geometric or analytic constructions. These are not algebraic over Q. So this is this can be done, it requires a proof. These are consequences of some theorems. They are transcendental over Q. So there is no polynomial for which have pi or e as roots, and various other elements one can write. On the other hand, pi and e are algebraic, so they are in R, right? Are algebraic over R, right? So this is where I am emphasizing the part about algebraic or transcendental are properties over a field. They are not intrinsic properties of an element. They are properties of an element with respect to a field. While there is no polynomial over Q which satisfies, which has pi or e as roots, there are polynomials over R. For example, you can take x minus p. pi, and you can take x minus e, which are both polynomials over R, and of course they have roots pi and e. When you substitute pi in the first polynomial, you get 0. When you substitute e in the second polynomial, you get 0. So they are algebraic over e, they are transcendental over q. So this is a good illustration of why it's very important to emphasize the base field. So whenever you have a field extension, the terminology is f is called the base field. So in all these considerations, base field is very important. Okay, so let me stop the video here. In this video we discussed the notion of subfields, field extensions, and we talked about the if you have a field extension and an element in the bigger field, we considered the construction of an intermediate field, which is the smallest field containing the base field and that element, and we explicitly described what the elements of that intermediate field are, f alpha, and we saw some examples, and we are ending with an important definition of the notion of algebraic and transcendental elements. And let me emphasize again, there is everything depends on the base field, because whether an element is algebraic or not depends on the base field. Pi is algebraic over R, but it's not algebraic over Q, it is transcendental over Q. So you have to keep stressing base field always. So let me stop the video here, and we'll continue in the next video with further study of algebraic extensions. Thank you.